In this lecture video, I would like to, or I'm going to discuss the wave functions of the hydrogen-like atoms. And so in a previous video, I described that it was more natural to write the wave functions in terms of the spherical polar coordinates, r, theta, phi. And the reason is because the problem, the differential equation, which is what Schrodinger's equation gives you, so that math problem is solvable by a separation of variables technique. And what that means is that you can solve the problem of Schrodinger's equation. Actually, Schrodinger's equation becomes three separate problems, where each problem is for a different variable because you can separate the variables. So this wave function psi, it can be written in terms of a radial part of the wave function, or a radial factor, multiplied by a factor. This is meant to be the capital letter theta. So it looks like an H written inside of a zero or an O. But that is the polar angle factor or part of the wave function. And then there is the azimuthal. So that's the capital letter phi. So this is it's the multiplication of three different functions, where each function is only a function of a single variable. That's the separation of variables sort of magic. And when you do this thing, what you find is that what you end up with is quantum numbers. And I alluded to in the previous video the fact that you get three different quantum numbers. A quantum number called n, a quantum number called L, and a third quantum number called m sub L. So it turns out that your wave functions, this is pretty interesting. So the wave function psi is specified by a selection of the quantum numbers, right? So we often write that psi is psi sub nl m sub l, right? So it's labeled by the quantum number. And r, right, the radial part of the wave function, or the radial factor, just depends on one of the quantum numbers. That is, the radial part of the wave function is what gives us the n values, and they are the principal quantum number. The theta function right here, or the theta factor, actually it depends on both quantum numbers. So it is a function of theta, but it's labeled by two different quantum numbers, L and m sub L. And then the factor phi only depends on that third quantum number. It's m sub L. Yeah, so the wave function is specified or selected for a choice of quantum numbers. And each of the factors in the separation of variables depends on the quantum numbers this way. And what's interesting is when you solve, so when you just do the math, so the math gives the quantum numbers, right? So for example, it tells us that the quantum number n can only take values that are integer, like this. So it's just doing the math that's going to give us the restriction that the label n is actually an integer. Another quality is L. L can only have the values from 0 up to n minus 1. That is L, the the choices that you have for L actually depend on your choice of n. And then m sub L is actually kind of similar. So m sub L can only go from minus L. Let me take that back just a second. So it can go from minus L to minus L minus 1. So that's so for example, if L is 5, you can have -5 or -4 or -3, right? All the way up through 0, all the way up to L on the other side. All right. And so here's an example. Actually, let me say, you can look up these functions. And the way that you will look them up is you just, for example, if you want to know the theta function, you need to ask for the theta function by asking for a particular combination of L and m sub L, right? So you can look these up in tables, right? Because mathematicians and physicists have basically written them all out, or written out the pattern, right? Sometimes when you look up these functions in tables, what you see is actually a combination called y, or sometimes it's referred to as y, and it'll be as a function of the pair of quantum numbers, L and m sub L, and it will be actually a function of theta and phi, because what it is actually the product of the polar angle factor and the azimuthal angle factor, where the polar angle factor, depends on the two quantum numbers, and the azimuthal angle factor only depends on the m sub L. But these things right here are referred to as spherical harmonics. They're really cool functions. They are, in a sense, they're referred to as a special function, and they solve the angular part of the Schrodinger equation, and they're called spherical harmonics. So if you're curious, if you're interested, you can go look up these spherical harmonics. So anyhow, let me ask a question real quick. So n equals to 2, L equals to 4, m sub L equals to -5. So this trio of quantum numbers might indicate a wave function whose principal quantum number is 2, angular momentum quantum number is 4, and this is called the projection of the angular momentum onto the z-axis quantum number is a -5. And this is impossible, right? Does not exist. And the reason is because these quantum numbers don't fit our restrictions. So if I start by saying the principal quantum number is a 2, then that means that the only available quantum numbers for angular momentum, or this L quantum number, is from 0 up to 2 minus 1, right? So that means L can actually only be 0 or 1. Also, m sub L, this third quantum number, its absolute magnitude cannot be bigger, right, than L itself, right? Because m sub L takes the quantum numbers from -L up to L. So if L is 4, then m sub L is only allowed to be -4, -3, -2, -1, or 0, or 1, 2, 3, or 4, right? So you have to be careful. There are restrictions. This wave function does not exist. But this wave function does exist. here's an interesting one. How about 2, 1, -1, right? So I can go look this up. The wave function for the hydrogen-like atom, psi sub 2, 1, comma, -1. I'm looking in a table right now. It's actually in the book for this class. So psi sub 2, 1, -1 is the following function. 1 over 8 times the square root of pi. And then 1 over a naught raised to 3/2. And then r over a naught. And then e raised to the minus r over twice a naught. And then sine of theta e to the minus I phi. Like this. So here's an example. This you would get from a table, right? So you just have to look it up, and you look it up by quantum number, and you can see that it is a function of r, theta, and phi. Here's phi. Let me change the color really quick. Or actually, let's use a little highlighter. There's phi. Here's theta. And r actually shows up in a few different places. There's another really interesting constant called a sub 0. And a sub 0 is a length. So this particular length is actually called the Bohr radius. And I'm looking for, actually I realized that I didn't get an expression for a sub 0 ready, but I'm just looking it up, right? Just like anybody else would look it up. Let's see, a sub 0. Sorry about that. A sub 0 is the Bohr radius. It would have been defined when you learned about the Bohr model of the hydrogen atom. So we get to recycle the meaning of this thing. And I just looked it up. I had to pause the recording. So a sub 0 is, in terms of fundamental constants, it's 4 pi epsilon naught h bar squared. So epsilon naught is the permittivity of free space. It comes from electrostatics, right? It's in the Coulomb potential. That's why epsilon naught is here. And then I divide by the mass of the electron. This is the electron's mass. And then I multiply by the fundamental charge squared. And if you calculate this out, it's about 0.0529 nanometers. It's a distance. This distance is made out of these fundamental constants. And so it's more convenient to sort of recognize this as a distance. And instead of writing down all of these constants, raised to the 3/2 underneath the 1, or underneath the r, or, underneath the r in the exponent, let's just recognize its importance. Its value is about that value. And so the wave function is given a distance scale. It's sort of like a scale to pay attention to, a distance that's important, right? About 0.05 nanometers. All right, but here's our wave function. So here's our wave function. R, theta, and phi, you can see the explicit dependencies, right? So let me remind you of how this fits into Schrodinger's equation. So Schrodinger's equation in r, theta, phi coordinates, it looks like the following thing. It's minus h bar squared over 2m. And then I referred to this operator as the Laplacian operator. And written in spherical polar coordinates, it looked like the following thing. So I put a big old square bracket. it's 1 over r squared, and then d squared, or no, actually it's d by dr. Yeah, excuse me. So there's not a square on this derivative. It's d by dr of the quantity r squared times d by dr, right? And then plus 1 over r squared sine of theta, and then d by d theta sine of theta d by d theta. So that's, yeah, and then there's a third term in the Laplacian operator. It's 1 over r squared sine squared of theta, and then d squared by d phi squared. Right? And this operator is meant to operate on psi, and it's equal to, or actually, sorry, but don't forget that you have to subtract off 1 over, or it's z e squared over 4 pi epsilon naught, 1 over r times the wave function psi, and it's equal to the energy times psi, right? Okay, so I want to point out how this Laplacian works. So if you look at, for example, this part right here, this part of the operator has just a double derivative in phi, right? So all this is going to do is take 1 over r squared sine squared of theta and multiply it by the second derivative with respect to phi. So that's easy. But here's one that's slightly more complicated. For example, let's look at the r. So this part of the Laplacian. So what's got to happen is, actually, let me take this. All right. So the way this works, 1 over r squared d by dr of r squared d by dr, this is operating on psi. And what this looks like, you have to be pretty careful, is it's got a product rule problem, right? So what we need to do is do 1 over r squared, take d by dr of r squared d psi by dr, right? This is how the operator is going to work. So if you follow this through a little bit, so 1 over r squared, so the derivative's got to do the product rule, right? So it's 1 over r squared times, and I'll do the product rule, it's twice r, right? So d by dr of r is 1, so it multiplies d psi by dr. But there's a second term where the derivative skips the first factor and hits the second factor. So it's plus r squared d squared psi by dr squared, right? And then you can imagine multiplying the 1 over r squared through, and I think you can see how this works. But the reason I bring this up is this is how you use these derivative operators, right? So you just imagine letting the operator, right, so this part, just act on it. But you have to imagine putting the wave function psi against, for example, the d by d theta, multiply by sine of theta, and then take the d by d theta of that product. So that's how it's written, right? So if you wanted to, and I think you should, what you can do is actually take this wave function, right, and figure out the energy. Because I'm telling you that this is a wave function right here. You can see all the bits and pieces, right? Everything is there. Here is the big operator. Here's the potential energy term. And what you can find is that if you do the problem, you can go and get the energy associated with these quantum numbers. And what you're going to find is that the energy of the wave function, so n equals to 2, L equals to 1, m sub L equals to minus 1, it actually does not depend on L and m sub L. It only depends on the principal quantum number, E sub 2, and you will just essentially reproduce the energy for the second level, so, or the first excited state, right? So E sub 2, or actually, let me back off a second. So E sub n is equal to, so it's minus m sub E, and then I guess, so I'm looking at something on the internet right now, or I'm looking at your book. So over twice h bar squared, and then 4 pi epsilon naught squared on the bottom, like this. And then it's, right? So these are the energies. So for example, E sub 2, right? You just put a 2 in for the n, so you get a 1/4, right? So you can get minus m sub e to the 4th over 8 h bar squared, right? So n is 2 for n equals to 2. So 1 over 2 squared is a 4, and that 4 hits that 2 and makes that 8. And then separately, I've got 4 pi epsilon naught all squared on the bottom. And what I think would be really cool for you to do right after you finish this video is go and make sure that if you take the Schrodinger equation and you take this answer, which is an n equals to 2 answer, that when you do Schrodinger's equation, you just do everything on the left-hand side of this equal sign right here. What you're going to find is your wave function right here multiplied by this, right? Your wave function is multiplied by E sub 2. If you can do that, then I think you should feel very confident that you have a basic understanding of what's going on. And also, you are reinforced in the sense that you can feel comfortable and confident that you know how the math is working out. This should be considered a simple exercise. It's algebraically intensive, and it will take you a whole sheet of paper. But you have to be very, coordinated and efficient and organized. If you're not organized, you'll lose track, and you won't feel confident, and you don't really understand what you're doing. So this is a self-check. I suggest you go and do that. But this formula right here, E sub n, is an important formula. So this is important. Those are the energies of the various wave functions. You notice that they do not depend on the quantum numbers m sub L and L. So the energies do not depend on the other two quantum numbers, only n, right? And this actually is the same as Bohr's prediction. And I'll just put an exclamation point. And the truth is, in a sense, it's a lucky coincidence. Because remember, Bohr's prediction of the hydrogen spectrum was spot on, right? He got the right answer for the energies, but the underlying physics is not correct, right? First of all, the underlying physics was only two-dimensional, and also, yeah, it's not fundamental enough. But this solution, which is based on solving this Schrodinger equation right here, is fundamental. It's fundamentally three-dimensional. It's fundamentally a quantum mechanical exercise. Bohr's exercise was called semi-classical. Yeah, okay. So in the next video, I'm going to describe L and M sub L and what physics are we getting there? And let me give you a warning. It's strange. Yeah, but this right here, let me give you a hint. This is the quantization of angular momentum. But instead of it being a hypothesis, which it was for Bohr, we get quantization of angular momentum as a byproduct of the Schrodinger equation. That is, the Schrodinger equation predicts that angular momentum is quantized. It's not a hypothesis, it's not an axiom that goes into the theory, it's actually just a byproduct. Just like energy quantization is a byproduct of Schrodinger's equation. So we're not asking for quantization of stuff. Schrodinger's equation is forcing it on us. So it's a fundamental quality of its prediction, right?